So the first paper I'd like to talk about today is entitled A Long-Distance Quantum-Capable Internet Testbed. And this is a paper from Stony Brook, Qunnect, and Brookhaven National Lab. So it's really bringing together industry, national lab, and university. This paper is showing a really great advance in long-distance quantum network implementation and control, and specifically in the areas of integrating some classical network concepts like a network stack. So what they're doing in this paper, they are producing two telecom photons using two separate quantum memories. And they are sending these photons over a distance of 158 kilometers to be interfered via HOM interference. And they're demonstrating this HOM interference between these two photons. This work is using room temperature quantum memories, specifically rubidium vapor cells. In this work, they're also using or implementing quantum frequency conversion between telecom and near IR. So some of these challenges that they're addressing in this paper are implementation of a long distance quantum network. The distance that these photons are traveling over is 158 kilometers. Also, creation of a quantum network stack and quantum network orchestrator, which is really bringing in some existing classical networking concepts as well to the quantum networking world. And then also polarization, compensation, and time synchronization implementation, of course. So these are just some of these challenges that are being attacked in this paper. So I'd like to kind of focus on one of the figures from this paper. So this figure is showing a quantum network stack schematic and showing how they're incorporating some classical networking into their quantum network. So in this schematic, we can see there's three layers. There is a classical network layer. This layer has different components, including white rabbit switch, multiplexer, orchestrator, node controllers, network switches, and these are all sending like TCP/IP signals and sending classical signals for controlling this quantum network. Underneath this layer, there's the quantum enabling network layer, which contains polarization control and compensation and preparation. So this is a layer which is kind of bridging this interface between this classical network layer and this quantum network layer. And then the final layer is the quantum network layer. In this layer, we have our rubidium vapor cell quantum memories, and we have our photons, which we are using for our HOM interference. And our HOM interference is performed on this layer as well as the quantum frequency transduction. Just to note, in this particular network architecture, they're sending the quantum signals over one fiber and classical signals over another separate fiber. So another figure I wanted to highlight from this paper is showing their polarization compensation. So in this figure, on the x-axis, we can see time of day, and on the y-axis of the upper three plots, we're seeing the Stokes parameter of the photon polarization state, and in the bottom plot is the fidelity of the state on the photon. So what we can see from this plot is during kind of nighttime hours, the fidelity is quite high. There aren't too many fluctuations in the Stokes parameter. And basically, we're seeing that there aren't too many perturbations to the quantum state that the photon is carrying. However, during the day, we're seeing a lot of drops in fidelity. And what's happening is many kilometers of fiber for this network is actually laid over, of the optical fiber is laid over or along roads. And so during the day, when people are out driving their cars, there are small changes in temperature and pressure that are perturbing the fibers, and even these tiny fluctuations are able to basically hurt the state, the polarization state on the photon. However, if you look closely, you can see every 15 minutes, the fidelity goes back up to approximately 1, and this is because they are using Qunnect's polarization compensator to correct for these drifts in polarization that can occur. So this is really able to really compensate for these drifts quite well. So to sum up this paper overall, it's a great advance in long-distance quantum network implementation using room temperature quantum memories, and also incorporating polarization compensation and of course time synchronization and some classical networking concepts and tools as well.